Hello, my name is Yulia. I am a PhD candidate at the Xiang Technological University. Now I will present you my project that is devoted to investigation of a particular two-dimensional perovskite under high pressure. Here is the outline of the presentation. First, I will start with the introduction and tell what is so special about this very two-dimensional perovskite and what is this class of materials in general. And then I will present the high pressure technique, since this is not a very well-known technique. And the second part of the presentation will be devoted to the results and discussion, and then conclusions. Let's start with introduction. Hybrid halide perovskite materials are known since about 10 years ago, and they have attracted a lot of attention. Many groups in the world study them because they were found to be very promising for solar cell application, and then also to applications in different fields like light emission, lasing, spintronics, and so on. And one of their advantages is their tunable properties. Depending on the composition, dimensionality of these materials, we can get materials with the properties we want. And remember about tunability, because this is one of the main points of the work that I'm presenting. And as I say, one of the ways to tune the properties is to change its dimensionality. By chemical methods, we can cut the materials along one of the crystallographic planes and get two-dimensional materials or one-dimensional materials and so on, with different orientations of the layers. Now let's move to the high pressure technique. Why do we need to use it for? Because when I say high pressure technique, this is really high pressure. This is up to 1 million atmospheres. It's clear that on the surface where we use it, we can never reach this pressure. However, this is a very important tool that has two main reasons or applications. First of all, under high pressure, we can find some properties that can't be achieved at ambient conditions yet. So this can work as a guide for designing of new materials that may have these properties even under ambient conditions. For example, recently there was found a near room temperature superconductor, but under very high pressure. And the second way is high pressure synthesis, high pressure treatment of the materials that can also help us to get something useful for applications. And the second question is how do we achieve high pressure technique and how we measure its properties in situ. We use a device called diamond anvil cell. Its photograph is shown here, and here is its skin. So there are two diamonds that are pushed towards each other, and there is a gasket. It's a piece of steel with a hole inside, and this hole, together with the two diamonds, form the chamber where the sample is loaded, together with ruby that is used as a reference to measure the pressure inside. This is how it looks if we take a micro photograph. In this case, these two crystals are our material under investigation, and this is ruby. So we measure luminescence of ruby to learn what is the pressure inside. Now let us start about this material that this work is devoted for. This is this perovskite. As I mentioned, it is 2D perovskite, so it consists of the inorganic perovskite layers that are separated by a very thick, very long organic cations. And in our case, the important moment is that these organic molecule, mechanical properties of this organic cation and inorganic layers are very different. Inorganic is relatively rigid, organic is very soft. So compression or even hydrostatic pressure will affect differently the soft organic and rigid inorganic layers. And this slide is already devoted to high pressure response of this material. In figure 8, you can see how how the crystal changes visually under pressure. Starting with yellow, it becomes darker, 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 and after 7 to 20 dpa, it looks, in fact, black. And these two graphs, they represent the respective optical absorption and photoluminescence spectra. The interesting part here that looks like after some pressure, about 1.5 dpa, there are two peaks that coexist in this structure. It can be different phases coexisting or defects, but we will discuss the origin of the second or third components later. In general, with compression, we see redshift of the optical properties, that is first related to the change of the angle and then related to the shortening of the PBI bond. At a relatively low pressure, around 0.7, 0.8 GPa, there is a phase transition that we have proved by Raman spectroscopy that show the changes in vibrations. The first graph shows the changes appearing in the inorganic sublattice. It's quite clear that this peak disappears around this pressure. The pattern of the peaks in the low frequency range also changes. Similar changes can be seen from the organic vibrations. That means that the phase transition also involves changes in the organic chain. From the similar materials, we know that this transition is related to the bending of the C16 chain. Ambient condition is straight, and high pressure makes it bended. And at the same pressure, there is a step-like change of the optical properties, both in optical absorption and photoluminescence. But the most interesting part, we noticed that after about 1.5 GPa, the material behavior is really unexpected and different from the other perovskite. First, let's start at 0 GPa before compression. We can see that both all color from the optical image, photoluminescence intensity mapping, and positioning of the PL peak mapping looks quite uniform. There is some difference in intensity, not very significant, that may be related to the surface quality or thickness of the crystal. However, after compression, we can see that first, the intensity is different from different parts of the crystal, and it isn't related to how the intensity was distributed before compression. So this difference is new. And what is more interesting is the positioning of the PL peak is different. The different colors in figure C represents the peak position. So in this case, we have the difference up to 50 or even 100 nanometers under the very same pressure. With the continuous pressure increase, this domain-like structure is conserved, and the separation between the different domains in terms of photoluminescence energy is even increased. And another interesting conclusion we can make here is that even after decompression, the crystal not the entire crystal comes back to its original photoluminescence. Some part of the crystal still have some additional components with lower energy. In the next slide, you can see the corresponding photoluminescence spectra. At 0 GPa, there is a slight variation of intensity, however, the peak position is same. And after 3.2 GPa, we have at least 3 or even more components. And the contributions of the components depend on from which domain we measure the spectrum. And here the separation is almost 100 nanometers, and here at a high pressure it is even more. And after decompression, some parts of the crystal emit the additional lower energy component. So here again, what happens after pressure release? We repeated this experiment several times, and always some parts of the crystal after compression, the luminescence came back to what it was before compression, and some were very different. And then we can compare it to some other 2D perovskites. For example, this one structure shown here is phenylthermonium lead iodide. After compression, the luminescence is completely uniform. We assumed that the different optical properties were caused by their differences in the crystal structure. To test this hypothesis, we performed Raman spectroscopy. In this slide, you can see PL measured from 2 domains with very different properties, shown in green and orange lines here, and the organic spectra from these 2 corresponding domains. This spectrum comes from the inorganic vibrations, and we can see that there is an additional peak appearing when there is a redshifted PL. And the difference also appears in the vibrations of the organic molecule. Some peaks shifted, and in some pieces the intensity is different due to different contribution of the particular bands. A similar analysis was performed for their 2 different types of domains appearing after the pressure was released. The blue line corresponds to the reversible part, the red line is irreversible part, black is before compression. The reversible part, the Raman spectra from both organic and inorganic parts look similar. However, the irreversible part, the vibrations are different, shifted, and similarly the new peak may appear. That shows that the structures of these 2 domains are also different. We proposed a theory that can explain the phenomenon that we have seen from the experiment. First of all, let's say that we know that the optical properties are determined by the structure of the inorganic sublattice. Then why the properties of this material that is only different with the organic part are so unique? Before compression, the schematically structure is shown here. The blue line is the inorganic layer, and this is organic molecules. Initially, they are straight. Then we know that for similar materials, during the first phase transition, a bending of these molecules happening. So the organic cation is in a different conformation. Our molecule is very long. It has 16 carbon atoms in the chain. And that's why it has a lot of degrees of freedom on how exactly this bending can happen. One of the ideas how different it can happen is that at one molecule it happens on the 3rd carbon atom, and at the other molecule it happens on the 2nd carbon atoms. So in different parts of the crystal, randomly, we have different conformations of the organic molecule. The organic molecule is bonded with the inorganic. So different conformations of the organic part will cause different octahedra tilting, different octahedra distortions in the inorganic layer. That will be reflected in the band structure that is determined by these lead and iodine orbitals. And different parts in the crystals from the point of structure will correspond to different band structures that are shown in the bottom part of the slide. And finally, after decompression, again, depending on how these conformations of the organic molecule happen under compression, some parts of the crystal can exhibit reversible transition. The other part of the crystal exhibit irreversible transition. So, conclusions. We have a phase transition in this material that's happening at relatively low pressure in comparison with other 2D perovskite with shorter chains. Then we have seen an unusual response under high pressure with different random domains exhibiting variable vibrational and optical properties. And this variation sometimes is conserved after pressure release, sometimes the transition is completely reversible. And what all this means? It means that in this material, under pressure, we have an additional way of tunability beside the composition. The very same material under the very same condition can show variable properties. And this can raise a question whether we can control and achieve this phenomenon under ambient condition. Because if we can, in the very same material, we can, for example, achieve a p-n junction without any contact, any use of two different materials. And that can be very useful for applications. Thank you for your attention. If you have any questions, you can probably ask them. Yeah. Goodbye.